Thank you all for being here. As a reminder, you can ask questions in the Track General Slack. We'll start a thread there for that. And our second talk is can there be too much parallel? So Thomas, can there be too much parallelism?
Can there?
And then for the AirMeet people, if you ever have trouble, the AV people do monitor the AirMeet, so you can just ask questions directly in the AirMeet if there's troubles with the stream. In-person questions will be in person. Yeah. We have a floating mic. Yeah.
Thank you for the introduction. So I'm Thomas. I'm a software engineer at Quantsite Labs. Today, we're going to answer this question, or try to answer this question of, can there be too much parallelism? And to jump to the point, the answer is yes. That was not on purpose, but yes. But what do I mean by this? Like, this is a loaded question by design. And this means a lot of things to many people. And what I mean by this is, well, there's a lot of libraries out here that we use that try to engage in parallelism. And what happens when we use them in combination, or not in combination, or in general? But so to make this more concrete, here's a slide with lots of libraries out here. How many people have used one of these libraries? All right, cool, one, all right. How many people here have used more than two in one program? Cool, yeah, so this talk is for you, all of you. All right, so you more than two or three, yeah, and all the things you may run into when running these libraries together, because all of these libraries engage in parallelism in some way. And sometimes they don't play well together, and we're going to talk about this in this talk. Now, that's for users. Developers out here, or maintainers of a project on like PyPI, on Conda Forge, or Conda, how many people have a library that depends on any of these libraries? More than one. So like, this happens. And then that means you inherit the semantics of parallelism in each of these libraries. And you have to work around them, so to say. So my perspective is that I'm a maintainer for scikit-learn. We have lots of parallelism going on in this library, such as we use BLAST from NumPy and SciPy. Internally, we use OpenMP with Python, which is its own flavor of parallelism. We also have Python multi-threading and Python multiprocessing. And so we do run into many issues from our users because we engage in so many forms of parallelism. So this talk is a accumulation of years of going through issues and triaging and figuring out what's going on with our users when they use scikit-learn and something stalls, freezes, takes forever, crashes. And so I'm hoping all the knowledge from this talk, I'm sharing all the knowledge I've gained from this talk in this talk with you. So hope y'all learned something. So to define the scope of this talk, I'm gonna narrow it down to CPU-based parallelism, so things that run on your laptop, or also, and not GPUs, so laptops, CPUs. Not clusters, so I'm not going to talk about clustering, and very focused on Python. So parallelism for Python, which is why we're all here. This is SciPy. So in a broad sense, this is how I see the state of parallelism in Python. These are the three broad topics that we have to engage with. APIs, which is how libraries allow you to configure the level of parallelism in these libraries. Next is interactions. This is how parallel libraries interact with each other, or don't interact with each other, and all the nuances that could happen when you try to use native threading with Python multiprocessing, and all the things that can happen when you try to mix together different forms of parallelism. And lastly, defaults. This is, if you do nothing, what does your library do? Does it use all the cores? Does it use one core? And we're going to go through a fun exercise at the end to go through this as well. So these are the three things I want to focus on when dealing with Python parallelism. So let's start with APIs. APIs, this is how we control. So libraries have different forms of ways to control how we tell it to use. Libraries have different ways to configure how much parallelism it uses. So there's different APIs. There's 4 big ones. The most common one, which is where I see in every machine learning engineer's code or everywhere, it's environment variables. There's the 3 popular ones. There's an OpenMP one. There's an MKL one, but that's for Intel. There's OpenBlast. There's also a bunch more. I could keep going. It's, if you use Polars, who knows Polars? Polars is a very cool library. Okay, cool. Woo, Polars. It's a very cool library for data frames. I'll talk more about it later. But they have each one of these have their own environment variables. And this is the most common one. This is the one that doesn't rely on Python. You set it in the environment and it just works. The other form is global configuration. Who used PyTorch here? PyTorch, very popular library. It has its own global function. NumPy has one. There's a library called DreadpoolCTL that has one. So these libraries expose a Python level function to configure parallelism. So that's global. Next, this is one special thing about DreadpoolCTL is that it allows you to have block configuration. So this is through Python's context manager. It allows you to specify a number of threads, something a block of code is using. And and DreadpoolCTL recognizes many different thread pools that libraries commonly use, like OpenBlast, MKL, OpenMP, Bliss. So it recognizes all these thread pools and configures them. And it does it internally. So it's very nice. This is context manager. And lastly, there's call sites. So for scikit-learn, there's njobs, SciPy, there's workers, PyTorch data loaders, num workers, and so forth. These are keyword arguments that you pass in the call site to configure parallelism. So, these are the 4 big ways. So these are the 4 big ways to configure parallelism, and there's a lot. So as a new user, you have to learn this. Like each one has a different API. There's a different API. Some libraries don't implement all of them. Some implement a subset, and we'll look at this when we look at defaults. And so it's a big landscape of APIs when it comes to configuring parallelism. So I have proposals in this talk about where I could see this being better, and how what is the better situation than we have now. And so now we have all these variables. This is very common in like the people that deploy with Java. So people have Java-based distributions that deploy Python code. And the only way to configure it is using environment variables, because that's if you want to control your Python program without using Python. So this is very common to like just keep on having exports. A good feature is use OMP num threads, because many libraries already recognize this. So OpenBlast and PyTorch all recognize this parameter, and then so if you set this one, that usually sets it for most of the things you care about. But you see that it's prefixed with OMP, so that's very specific to OpenMP. If we want a less pragmatic approach and a more generic approach, there's something called go-to num threads that's popularized by OpenBlast, and this configures. This is having a standard way to configure a number of threads in your Python program. That'd be very nice. This having go-to num threads doesn't mean you don't have your own special one for your library. It just has you just have one default one that you all look at. So for example, OpenBlast, if you have go-to num threads set and OpenBlast num thread set, it will use the OpenBlast one. But if you don't have, if you only have go-to num thread set, then it uses the go-to num threads one. So it has like a common default, which is very nice. Next proposal is DreadpoolCTL recognizes many different thread pools out there, the most common ones. There are a lot of thread pools that it doesn't recognize, And being able to update thread pool CTL to recognize more thread pools will make it very nice for libraries to control the level of parallelism in Python. So thread pool CTL has a global configuration flag and the block manager, the context manager. So it's very, very nice to if we can move forward to this. And it's very thread pool CTL. It's one file, so it's not too bad to contribute to. So it's just one file that does all this work. And lastly, call sites. There's different call sites. Scikit-learn has, libraries have different call site keyword parameters. It'd be nice if we can move forward and have everyone use one of them so that the APIs are consistent. So in general, this is calling for consistent APIs, which is a social issue. It's trying to push over so that everyone moves forward in a direction so that users could have a consistent API between these libraries in terms of parallelism. Okay, so that's APIs. Interactions. This is how libraries interact with each other when you have them installed and used together. And so this is there's a lot of nuances to this one because when you mix together multiple forms of parallelism, many things could go wrong. And I'll showcase a few of them here in this talk. There's an endless list of these things. So the most traditional one, the one that a lot of libraries already recognize is oversubscription. So in this example, we have SciPy optimize .brute. It has its workers parameter, so it has its own form of parallelism. And in this case, I set it to 8. So let's assume we have an 8-core machine here. And then you also pass it a function that also is parallel with 8 cores. So this is the classic example of oversubscription. You're giving your CPU too much work, and a lot of times it just stalls if you do this. It just never finishes. But this is a very common problem. People recognize this. Like when I've seen less and less people write this type of code because people recognize this is an oversubscription problem. Libraries like DAS, who uses DAS here? DAS is a very cool library, yeah? This is the docs. If you are trying to run DAS distributed, it recommends you set the environment variables to 1 so that you let DAS handle the parallelism. So it's a very common pattern. You see that it sets the environment variables that we discussed in the API section. In Ray is also a library that does that distributes work. It also recommends this. It's to set OMP num threads. PyTorch dayloader, using the dayloader uses multiprocessing, and then PyTorch itself is parallel because it uses OpenMP. So in the worker loop, PyTorch also sets the num threads. So this is when a library knows that it's going to be used in a way where you're going to nest parallelism, it always tries its best to configure the number of threads in the inner loop, basically. This is a fun one from scikit-learn. Histogram gradient boosting classifier is scikit-learn's version of LightGBM. By default, it's parallel. So it uses all the cores by default when you call fit on histogram gradient boosting classifier. Having grid search CV is our version, scikit-learn's version of successive halving. It also has the njobs parameter. So in this case, let's say 8 cores on my machine. And in this case, I'm running, this looks like oversubscription because 8 cores and then my histogram gradient boosting is also 8 cores, so this is oversubscribed. Well, by default, scikit-learn uses thread pool CTL to control the number of threads in the inner loop. So in this case, it doesn't oversubscribe. It configures the inner loop to have 1 thread. So if you have a library, if you're writing a library that anticipates this behavior, it's very good to use, have a way to configure the inner loop so that users don't run into stalling issues, because this is a very common, it was a common problem, but now this is the way we handle it. Having thread pool CTL recognize many threads, many thread pools, and allowing that to configure the inner loop. So that is the easier problem. Now the harder problem comes next. It's when you, it's not oversubscription in this case, it's when different parallel abstractions just don't work well together. They just, for one reason or another, they just crash or stall or just stop, and there's no warning. So one canonical case is that if you use Python multiprocessing using fork, which is the default on Linux, and you have a GCC version of OpenMP, OpenMP has many versions. Compiler implements different versions of OpenMP. If you use the specific flavor of OpenMP, it stalls. It just never finishes. Your program just stalls. If you have different flavors of OpenMP together on Linux, sometimes stalls. If you have multiple blasts installed, open blasts installed, like on PyPI, which I'll show in the future, later here, sometimes slower. So these are the issues that are in our issue tracker, and it's hard to debug because stalling and sometimes slower, depending on how you install and what you do, it's very hard to track down. And I wrote about this in a blog post, in this design doc that talks about all these ways of things that could go awry. And there's many different nuances to this. So for this talk, I'm going to talk about two of these. So multiple parallel abstractions. I took these screenshots from different libraries like Polars, NumPy, scikit-learn, Pandas, and they all talk about this issue of fundamentally the first issue. If you use fork multiprocessing and certain versions of if you use GCC OpenMP, stall. So we all write about this and how to avoid it. So we do document this issue because it's very common in our libraries. And so documentation, very important because it makes you aware. So very important. So I have proposals about how to make this better. There's a patch for GCC OpenMP. If anyone's in this ecosystem of GCC, there's this patch open in 2014 that fixes the issue. So if anyone has any movement in this community, it'd be nice to get this merged, and so that we don't have to run into the first issue. So they exist. NumPy catches issues early. So the fork issue with OpenMP is so common that NumPy has specific code to catch this issue and error out and raise, and then tell a user that this doesn't work. The issue with this is that it's very hard to catch every single issue when you run two parallel systems together. So, but it's a good bandage. Okay, so how many people here have used CI build wheel or ship things on PyPI? Yeah? So, and who have run something called audit wheel right afterwards to vendor things. So this is the picture from Ralph Gomer's talk about how vendors in threading libraries, or vendoring binaries. So at the top, you can see that scikit-learn. We use OpenMP, so we vendor in OpenMP. It's part of the wheel when you install from PyPI. SciPy and NumPy has also each individually vendors in OpenBlast. So in this picture, you could have multiple thread pools running. You could have scikit-learn's OpenMP thread pool running, and also OpenBlast thread pool running on the side. And this leads to fun issues, such as when you use multiple native thread pool libraries and you run them, in this case, not oversubscription. I'm just running them sequentially. So first, I'm using matrix multiply, which is a OpenBlast thing, and then I'm going to OpenMP, and then I'm iterating through them. So I'm going back and forth. So when OpenBlast runs uses its thread pool, it holds, after it's done its computation, the thread pool is waiting for more work. And that waiting keeps the CPU active and not allowing for the second line to run, which causes this thing to slow down. And this is a very common pattern in scikit-learn because we're doing some sort of math and waiting for convergence. So we're doing a loop. And so this is sometimes slower. It is slower for when you have multiple threading libraries when you use PyPI to install these libraries. The workaround that we have told our users is use Conda Forge or Conda, because they have a solution for this, and it looks like this. Well, instead of having everyone have their own thread pools, why not everyone use the same thread pool so they share this one single thread pool? So if you don't have this problem of multiple thread pools waiting, because you have one single thread pool, you give it all the work, and it's going to churn out, and it's going to do its computation. So this is the kind of forge model, and it's a workaround that we have. So proposal, kind of, ship OpenMP wheels and PyPI to mimic the Conda Forge situation. This is something Intel has done already. The issue with this is that this only supports OpenMP. Polars has its own way of doing parallelism using Rust and Rayon. SciPy FFT module uses P threads and C++, and that has its own specific thread pool. And so it's not a universal problem, but it's slightly closer to a solution because it's better than what we have now, basically. But it's still not a complete solution. It's not completely satisfactory. So that is interactions. Lastly, defaults. This is the happy path that people go down when they install their library and how the library, what the defaults are for your library when you install it without configuration. So this is the quick quiz. This is NumPy and np.sum. This is how many people this thinks that uses one core? One core? Or how many people think this is parallel? All right, so this is one core. All right. So no configuration. This is always single thread. This is one core by default. Matrix multiplication. This is using the @ symbol. All cores? All cores? Yes. Yes, all cores. Yes, this is all cores. I'm not gonna. All right, so this is all your cores. All right. This is NumPy. This is current behavior. I'm not gonna. So how to configure it? OMP num threads, because most of the libraries recognize this, or thread pool CTL. So 2 ways. PyTorch. Okay, PyTorch.sum is this single multi-core. This is multi-core. PyTorch is default multi-core. And so you configure it. There's many ways to configure it. OMP num threads, thread pool CTL. PyTorch also has a function. So pandas. Pandas are, I'm doing a rolling mean here. This is a giveaway, one core, because it's pandas. It's mostly all just single core. Pandas does have a way to use number. This is where you could pass an engine your number, and engine keywords parallel equal true. Based on what I wrote here, this is all cores, all right? Because it's using number as a backend. And configure it, number has its API. So pandas, because it's using number, inherits the semantics of number to configure itself. So number num threads, and number has a function. Scikit-learn logistic regression and calling .predict. How many of you think this is single-threaded? How many of you think this is multi-threaded? So this is multi-threaded because internally this uses matrix multiplication. And matrix multiplication in NumPy is multi-threaded. So to configure it, we inherit the NumPy semantics, and it's the same. This is the same as configuring matrix multiplication in NumPy. So this is what it looks like now. This is how you configure parallelism in Python at the moment. Hidden gradient boosting. This is multi-threaded. This is OpenMP, environment variables, and thread pool CTL. All right. So Polars. This is Polars has a very nice. It has lazy data frames. It's built on Rust, and it has also Eagle data frames. This is a way to do lazy data frames, and I'm doing a group by, and this is multi-threaded using Rust and Rayon. So, and then configuration only has one configuration option, environment variables. And so I could do this exercise continuously, but this is like a landscape of items where most of the libraries out there are trying to use all the cores on your machine, and it's not consistent behavior. So maybe we could agree on a default. Maybe. I think this is hard because the default for all parallel is very good for the use case of interactive. If you're working with your library interactively, you wanted to use all your machine all at once. But if you're a MOE, a machine learning engineer, or a system engineer, you want it to be single-threaded so that you could reason about it easier when you deploy this work. So it's very hard to agree on a default. It'll be easier if we have a consistent API. if there's a consistent API, then maybe we could have all cores at default, and because it's very easy to configure these libraries. So that's one proposal. The other one is the libraries we use already. Document how you configure parallelism in your library, and that's the easy solution. All right, so state of parallelism, APIs, interaction, and defaults. So there's the APIs and defaults are more social issues where we want to move libraries together and have a common interface. Interactions is a harder one. It's a technical issue where different forms of parallelism just don't interact well together. And so that's why I see it as a state of parallelism. If I circle back all the way to the beginning, can there be too much parallelism? The answer was yes. I do wish the answer will be no in the future, where users can use libraries together, and it just works. And nothing stalls and whatnot. And developers, I want it to be easier for you to take advantage of parallelism and not run into all these issues that I mentioned in this talk. So all the material for this talk is available on GitHub. And thank you all for listening.
Thank you, Thomas. So our first question from the Slack is, when proposing new API terms that could be shared by all libraries, how do we get the libraries to adopt them? Otherwise, we will just have more terms than before.
So in the current way to do it is to do the scientific Python process, enhancement proposal process, where there's something called specs, and that we could write a document that has a uniform API, have an API, and then have projects endorse it and then adopt it. The hard part is probably getting everyone to agree on the keywords.
Yeah, so in the situation where you have like sort of these nested thread pools, and the recommended solution is always to just disable the inner thread pool, is it ever the situation where it would actually be better to disable the outer thread pool and that the inner thread pool manager would do a better job?
Okay, so sometimes it's beneficial. We've seen it in scikit-learn, where it's sometimes beneficial to allow the inner one to be multi-threaded and the outer one to be not, but it depends on what you're running. Sometimes it's better, sometimes it's worse. Sorry.
Are you looking at something?
No, that's okay.
Okay. So you proposed installing OpenMP from PyPI. David thought that one PyPI package can't make C calls to another one.
Ooh, okay. So that's a technical issue. You could, I haven't.
He mentions that Conda does solve this, but.
Yes, it's a technical issue. No. Yeah, it's an issue.
Oh, yeah. First of all, a very nice talk. Thanks for outlining all the pain points. It looks like you're still looking for solutions. So in the recent days, there has been this discussion on the Threads app, no pun intended, but about multi-threading in Python, enabling it there. And Meta pledged somehow like to donate, or not donate, but to have engineers working on that. Would that give you more like headaches because it's even another thing that has threading, or would it make life easier if Python had some more natural way of doing that? Because you would have to re-engineer a lot of things, but maybe it's for the better. Is it for the worse? What is your opinion on that?
So I'm thinking you're talking about the no-gil work.
Yeah. Is this at all related, or?
It's related. I have a slide on it. Looks promising, but hard to lift because it's hard. When I follow the thread and the discussion, we need to try it out. I'm not sure. Probably no-gil will work, but scikit-learn does run CI on the no-gil version of Python, and it works. We're not sure if it's faster or not. So in scikit-learn, in terms of scikit-learn, the uplift is 0 because we already test on this version, on the meta Python no-gil version. that they're developing. So we're not sure. I'm unsure of the future of this thing, but yeah.
Hi, nice talk. I had a quick question about if there's any kind of like resource profiling tools that you're aware of, because a lot of times you want to know, like, am I hitting these edge cases where I'm like oversubscribing, or like is my code working as I expect it to?
There's a lot. Every few months I find another one, but the traditional, the ones I usually use is PySpy. So if you're profiling, I'm guessing if the question is if you want to profile your parallel code, I usually turn this PySpy and it works.
So as a Conda user, it looks like I'm halfway there to the solution. And the second aspect of the solution, though, is all of these environment variables. And so I'd like to have my developer or my developers and users of my systems have an easy way to have made the right choices. So is somebody going to make a Conda package that will set my environment variables for me? Set to reasonable defaults. That's what I want, is reasonable defaults. You guys are the experts. I don't want to have to be an expert to not get in trouble. I want to try to avoid trouble. Do you think you can do that for me, please?
It's
Please?
technically possible. Because Conda, one of the things it does is set environment variables. So it could technically create a Conda package that only sets environment variables.
Okay, this is going into curse territory now. Let's thank our speaker again.